Yeah, today I will be talking about closing the gap and what that actually means in the context of 1 micron resolution data and how generative AI can help us. Cool. Sorry, the podium just started moving. So with the big brain that we all know, that we're all here for, we are actually working on 1 micron data. And as we've seen in the talk by Katrin this morning, there are some artifacts arising during the pre-processing of the data, so the cutting procedures or the staining. And of course, we want to get rid of them. And for that, we need to have some kind of artifact correction. For the big brain at the 20 micron resolution, this was done in very labor-intensive manual corrections. And this sadly doesn't scale from 1 micron, so we need to have an automatic solution for this. And the best solution that we probably will have for this is generative AI combined with a very good evaluation method behind that. And luckily, last year we released a model that can actually fill such gaps, in this case an artificial black hole in the middle of the section, where the diffusion model generates, based on noise, conditioned on the intact areas, new tissue. And I will play the video now, then you can see this better. And yeah, I assume that, especially for the distance, you can see no difference. And this is due to that the model generating very high and realistic texture and plausible cell statistics. So it actually looks not only like real tissue, but it also is on the statistics level like real tissue. Problem with this is that histology is actually 3D and not 2D, so we don't have just a bunch of sections, but we actually had some time ago a full brain. And with this naive approach of a diffusion model working on sections, we leave out a lot of information that is actually there in the structure. And in addition, if we have a section completely missing, there's no anchor for the inpainting for the model. So if we do like a quick little test, we just remove every second section, or the middle part of every second section, and just let it rerun with our diffusion model that we proposed. We can see that the blood vessel here on the right that we had now is completely broken with gray bars in the middle, where actually blood vessel should have been. Of course, the answer is rather simple in the idea. Just look at the section above and below because the blood vessel is there and just try to copy it from there somehow. And this is where the multi-branch diffusion model comes in, where we actually try to generate 3 consecutive patches at once based on some noise. And it's quite simple, the idea, we start with our naive diffusion model in the middle, generating 1 patch. We just duplicate it 2 more times. Now we have 3 patches, which are at the moment independent of each other. So we just add some communication in the form of cross-attention for the ones that know what it is, and we can get 3 consecutive coherent patches at once. And if we look back at the example, this was the naive approach with the gray bars. If we go now to the multi-branch attention, we get back our nice blood vessel going over the whole stack. Yeah, now this is all nice and looks good. But again, at the beginning, I said we need some good evaluation. And the nice thing about going to 1 micron data is that we have very high precise precision, and we can actually look at the cells, so we can count cells. The basic approach here is we take our original image, we remove some parts of it randomly with some fixed mask size. We then generate some new data with our model for this, and then we get some analysis models. These are downstream tasks. So for example, brain area classification or cell segmentation. And this model can predict or give some judgment about plausibility. I brought 2 models to bring this home, bring this point a bit closer to you. And the first one is the CPN developed by Eric Upschulte in our group, which just takes the 2 patches, the generated and original, produces the cell segmentations for this. We can then compute the cell density on these patches and just compare it between original and generated. And we would assume the better the model, the closer this should be to the ground truth. And here we can see that with varying masking percentages, so from 5% to 85%, the multi-branch diffusion achieves much lower scores in deviation. The second model, downstream task, is the CytoNet. Christian will talk about this, I think, in 2 talks or something like this, so very close, which is a brain foundation model, but one of its many applications is area classification. So we can put in an image patch of a cortical area, and it will give us the cortical area up to a very high precision. And here again, we use the generated original data and compare the classification. And if it's consistent, then it's good. And if it's not consistent, then it's bad. And again, here with the masking percentage varying, we can see that the multi-branch diffusion, especially for high masking percentages, improves the consistency greatly. Now, now that we've seen the evaluation part, let's have a look at some real-life example. Here I brought 3 consecutive sections with the one in the middle having a rather large rip, and we would like to fix that. In order to do that, first we align the 3 sections together. This uses light glue and some polyfan transformations, which have been developed in-house with Marcel and me. And the interesting part about this example is that we actually have 3 more smaller artifacts that actually occur over all 3 consecutive sections at once. So here we can't just copy the data from one section to the other, but we actually have to generate it simultaneously at once. And if we do that, it actually works simultaneously in plane artifacts and consecutive over multiple sections, consistent and coherent. Yeah, with that, we can say that multi-branch diffusion is closing the gap between 2D sections and actually 3D architecture, and it's moving towards automatic generation and very plausible tissue generation. The last point here is closing the gap towards seamless visualization, because we can just press a button and show either the original artifact version or the corrected version, so everybody can choose what they want to see and which they want to work with. With visualization, Alex will talk about Tiamat later and show you a little bit more about that. It also allows for interactive artifact correction, so you can put up a section, mask out like an artifact, and let it inpaint that. And with the 1 micron resolution, we can have a really nice quantitative variation. Moving forward, we are working on crossing the gap to modalities or different modalities. So this is, on the one hand, working on different modalities, each by themselves, but also cross-generating, for example, from cytoarchitecture to fiber architecture to immunohistology, all this stuff in basically one model. Yeah, then thank you for your attention, and thanks to all my colleagues and collaborators.